Thanks, Sam, and thank you all for attending my talk, taking time to come to this talk. This talk will be actually about secret key exchange and using wireless trading to generate the secret key, and our focus will be on understanding the efficiency of this whole process when there is an active adversary involved in the setup. And this is joint work with my colleagues Darshi Agarwal and Hakar Srivatsa at IBM Research. So what I thought was that before I get into details of the talk, just give you a quick overview of the kind of stuff that we do at IBM, more specifically within the department I'm in. And there are actually two broad focus that we have. One is on wireless networks, and the other is on cloud computing. So on the wireless network side, there's a significant project, a big project that we are involved with. It's between the US and the UK. It's sponsored by the US and UK Army, and it's called the International Technology Alliance. It's a big consortium of around 20 institutions, and our department is actually the lead on this whole consortium. Because it's a joint program between the US and UK, the focus is on coalition networks where multiple organizations have to operate together and get this, have achieve goals. But the focus, but the kind of the scope of this program is quite broad. We have research that goes on in network theory to security of systems to even sensor systems and information management. So there's a broad scope of this program. The other focus is on cloud computing, and here again we have a research program with NIST, the National Institute of Science and Technology, and it's called the Measurement Science of Cloud Computing. Essentially, the idea here is that is to study problems, various different problems in cloud computing. Some of the issues that myself and some of the other colleagues have looked at is things like placement of VMs in data center resource allocation, or you want to do scheduling of jobs within the data center, as well as some work on utilizing these on-demand cloud resources, which sort of fluctuate over time, sort of the spare capacity in the data center. So this talk, I will focus on, so the work that I've talked about in this talk was done as part of the ITA program. So let me now get into the details. Let me start setting up the problem. As I said before, this is about secret key exchange. So the first question is, it's a very, very basic question, but let's start with that. What is secret key exchange? So essentially, the idea is that you have three nodes, node A, node B, and node E, which are also referred to as, and which are classically also referred to as Alice, Bob, and Eve. The idea is that Alice and Bob want to exchange a secret key, essentially a secret number between themselves. And the idea is that adversary should know nothing about this secret key. And the secret key would be used by these two devices to enable many security functions at higher layer. I don't have to go into details. I mean, you can have data encryption, file layer encryption, etc. Now, there are two broad ways in which you can do this. Essentially, one is pre-shared, where the two nodes get together, a priori share the secret key, and then they're done. The thing is that this can be done in, let's say, networks which are small and where you have full control over the devices. But if you're talking about devices or networks which are much bigger, thousands of devices, then really the solution will not scale. And so there's this other whole stream of work where you want to exchange the secret keys on demand. And the idea is that you will actually use some physical messages. The A and B will actually send public messages to each other and then try to generate a key out of that. Again, there are two broad philosophies here. How you would actually do this key exchange. One is this computational security-based philosophy, where the assumption is that there are certain hard math problems which cannot be solved in a limited time with limited computation. And the idea is that any adversary, any practical adversary would have such computation limit. Example here is the Hellman key exchange, the straight log based Hellman key exchange. The other philosophy is this information-theoretic key exchange, where you do not impose any restriction on the computation capability of the adversary. But the way you would actually exchange or you generate a secret key is through common randomness. So the idea is that A and B somehow have some common randomness that they use to get a key from. So this talk, we will not try to actually argue about one philosophy or the other, but we'll just focus on this information-theoretic key exchange, and more specifically, key exchange using common randomness generated from parallel security. So, okay. So the next question is, before I actually go into more details, how does wireless fading help in key exchange? And this figure is just an ideal situation which will give a good overview of how this will be done. So again, we have two devices, A and B, and let's consider the ideal situation where there is no noise or interference in the environment. And let's say let's just denote XA as the symbol that A transmits, XB the symbol that B transmits, Y the receive symbol at A, YB the receive symbol at node B. And so when A transmits, what node B will receive will be a faded symbol, which will be just HAB times XA, where HAB is the fading coefficient from A to B. Vice versa, for device A, the received symbol will be HBA times XB. Okay, this is fairly standard communication stuff. The idea here is that there are three important properties that you can utilize now, which will help you generate a secret key. The first is channel reciprocity. So the idea here is that the fading coefficient from A to B and from B to A are similar if you have identical transceivers at both nodes A and B, and if these transmissions happen very close in time. So you can sort of assume that the environment has not changed much, so that the fading coefficients in each direction are identical, almost identical. And the other property is channel randomness, which is that these fading coefficients that you would get over time are a random process. They are not a deterministic sequence, so an adversary cannot just generate them deterministically. And the third property is spatial independence, which is that the fading coefficient is a property of the two nodes. And so if you have an adversary which is not directly co-located at either node A or B, then the fading between node A and the adversary will be independent from the fading between A and B. So this is great. So now suppose if A and B just transmit a unit symbol, then they each receive this H fading coefficients. These fading coefficients are exactly identical in this ideal situation because of reciprocity. They are also a random process. They are a sequence of random variables. And because of independence, the adversary would not know, based on the measurements that it takes, what is the fading between A and B, because it's a property of the two nodes. And so once they have these two, they can use this whole sequence that they get to generate the key. Of course, in reality, you will have both noise and adversarial signal interference. And so what this will do is that it will break this perfect common randomness sharing that happens between A and B. And so you would have to actually go through additional steps before generating a secret key. And what these additional steps will do, these additional steps are nothing but message exchanges between node A and node B before they can generate a secret key. And these additional messages will sort of affect the efficiency of this whole process. And this talk will be about quantifying this thing. How does the efficiency change as a function of how much adversarial interference power that you have in the system.
So I have a question about the spatial independence property. Would an attacker be able to gain a little bit of information about the key, more so than another attacker, if they were close to the receiver, or is it where you're assuming it's kind of completely independent? If I'm not at that location, Or can I gain some information by getting closer?
I think what people have shown is that if you're just a few wavelengths away, then the channel completely becomes independent. And few wavelengths, we're talking about gigahertz, is just a few centimeters.
I see.
You really have to sit right there.
It depends on your baiting assumptions. Okay. If this is in free space, you have absolutely no privacy, no security. But if you're in like a wide sense stationary Lucis channel, then it is directly related to your wavelength. Because there are assumptions on the richness of the scattering environment.
Yes. So the idea is that there are a lot of scatters around. So now going back, just looking at the literature, there is the idea of using fading appeared about quite early, maybe about a decade or so back. But more recently, there has been a significant amount of work in this space, and what we actually observed in all of these works was that the focus had always been on a passive adversarial scenario, where the adversary is only trying to do eavesdropping. That is definitely a very important scenario to consider, but we also realize that it's also equally important to understand what happens when you actually have an active adversary in this whole setup. And just a quick review of what we actually observed, or what we actually concluded through the analysis, was that when you actually put in an active adversary in this whole process, then the efficiency of this process degrades very rapidly with the interference power put in by the adversary. And so this sort of provides insights on demarcating the regions or the scenarios where key exchange in its current form or in the way we do it would be efficient versus things where it would sort of start to become more and more inefficient. Okay. So I've been talking.
Can you define what you mean by an active adversary? Because it sounds right now like your definition of an active adversary is not someone who actually tries to manipulate the protocols, but is actually just trying to inject and raise noise level.
So I'll come to that. Actually, the analysis is on the adversary which raises the noise floor, and that itself would sort of highlight the kind of efficiency issues that I'm talking about. And then, if you actually go more and beyond, start to make the adversary more sophisticated, you'll sort of see more degradation. So
the second paper you listed actually talks about an active adversary that's actually trying to manipulate the protocol exchange. The one we come to, that was big paper. But did not consider raising the noise floor. Did discuss it, but did not consider it. But it was more focused on authentication challenges that an active adversary might introduce into the key exchange.
So I've been talking about efficiency of the key exchange process. Let me just quickly define it rigorously. So the idea here, or the motivation for this efficiency term or efficiency metric that we will look at, is from this communication cost versus key size trade-off. The idea here is that the whole process of key exchange will happen over an open wireless channel. And if you have an active adversary, then this whole communication, the communication cost of this whole process could be quite high. And that's because of smart jamming or message disruption attacks. And there are actually a wide range of such attacks which have been documented in the literature, where you can actually get the throughput to very low, extremely low throughputs by efficient attacks. Now you could actually employ some kind of anti-jamming modulation at the phi layer to evade such attacks, but the issue is that this kind of spectrum modulation requires the two nodes to actually share a secret key. And the assumption is that to begin with, they do not have such a key. So, and also if you look at from the adversary's perspective, this key exchange phase is sort of an important opportunity. In fact, the only opportunity for the adversary to sort of mount such disruption attacks. Because once the key gets exchanged, you could again, the two nodes could actually go to the spectral modulation, evade the adversary of the file layer, and you're done. And the adversary will have a much harder time to sort of now disrupt communication. So the observation from here is that if an efficient key exchange protocol must not only try to maximize the size of secret key, but it must also try to minimize the amount of message bits that you would need to exchange to generate the key. And so, deriving from this kind of motivation of this philosophy, we sort of said that let's look at this first order metric of performance, which is the ratio of total message size, total amount of information bits that need to be exchanged, divided by the size of the secret key that gets generated. It's essentially measuring the number of message bits per bit of secret key that you would, the number of message bits that you would need to exchange to generate one secret key. Okay, so with that, now let me start going into details of the kind of framework that we have and kind of assumptions that we make in this work. So this whole key exchange process will take, it's a three-step process. The first step is randomness sharing. Second step is information reconciliation and key extraction. Randomness sharing is the phase where two nodes A and B exchange these feeding coefficients or this randomness between themselves. Information reconciliation is the step where, because there is noise and other sorts of interference in the environment, they will try to correct their errors. The two streams that they have will not be exactly identical, so they will try to correct their errors. And then once these two steps are done, hopefully at the end of these two steps, nodes A and B will have the same random sequence, and then you will use that random sequence to extract the secret. So for this work, we're going to assume the following model, where again we have our three nodes, Alice, Bob, and Eve, and those are the feeding coefficients on each of the links. And so you can see that the signal, so let's say XA, XB, and XC are the symbols that A, B, and E transmit. Then the symbol that YA receives, Alice receives, is the faded symbol from B plus the faded symbol from E plus the noise term. And similarly for node B, the symbol that it receives is again the faded symbol from A, from E, and the noise term. Now, because of channel reciprocity, these fading coefficients we have assumed to be identical on either links. So it's just a pairwise property. And also because of spatial independence, all of these fading coefficients will be independent. Also, we'll assume a Rayleigh fading model so that these are Gaussian random variables. And we'll also do the following. We'll take XA and XB as 1. So A and B are just transmitting a unit symbol. And the idea here is that because in this first step, they are not trying to actually exchange some data bits between themselves. They are just trying to throw some energy into the environment and just collect these natural fading coefficients. And so, one is okay, transmitting symbol 1. And we will assume that the adversary E is just a simple jammer, which transmits a symbol alpha. So the interference power that it actually puts into the system is alpha squared. So coming back to your question, this is the specific model.
Ideal full duplex.
What?
Ideal full duplex.
Yes, for the adversary.
The protocol itself is ideal, because usually when we implement, we do half duplex. Alice goes to Bob, Bob goes to E, and there's the actual issue of the temporal coherence of the channel.
Yes. So yes, the idea here is that probably they're doing it within a coherence interval, but they are maybe doing it half and half. And this M could actually refer to the index of that entire interval. Okay. So now, when they come to the next step, which is information reconciliation, what Alice will do is that it will take its symbol stream Y and convert it into a discrete symbol stream. And then it will transmit some messages to Bob, such that using the received symbol vector YP, Bob and these messages M, Bob will be able to reconcile to the discrete symbol set of what Alice generated. So, so if you look at it, what Alice has to do is actually Alice has to send just enough messages to Bob such that with these messages and with its own symbol vector, Bob can get back back the discrete symbol set of Alice, and this is nothing but a distributed source coding problem. And so, using the Schlaping-Wolf result, you can come to the conclusion that the minimum size of the messages M that Alice must send to Bob is given by this conditional entropy term. Okay, so now once Alice has sent those messages to Bob, and assuming that Alice has sent sufficient number of messages, which is at least the conditional entropy of conditional entropy amount of messages, then Alice and Bob will both have this discrete symbol stream YAD, which I'm denoting there, after these first two steps. And then once they have this discrete symbol stream, they will try to extract a uniform secret key from that. And this can be done through the lots of techniques, privacy amplification. They use some kind of hashing to go from this discrete symbol to a secret key. The amount of key size that you can actually generate here is again bounded. The maximum size of the key that you can get here is this mutual information term, which is from Al-Sweep and Maurer, which is basically this entropy of YAD, discrete entropy of YAD minus its conditional entropy. So now, when we put all of these things together, what we see is that if we now let's go back and look at what is the efficiency which we have defined in terms of the amount of message bits that you need per bit of secret key size that gets established. Then we know that the minimum message size must be this conditional entropy term. So here I have actually neglected the amount of communication that's needed for the randomness sharing, because the idea here is that when you're doing randomness sharing, there is no encoding or decoding happening. It's Alice and Bob are just trying to insert some energy into the environment and trying to collect the received symbols. As opposed to information reconciliation, where they have to make sure that the messages go reliably to the other side. So, so this sort of part is the more costly part, because it has to have both encoding and decoding has to happen at both sides. And then for key extraction, again here this is sort of a very relatively less costly step, because you might just have to exchange maybe the index of the hash function. So the minimum size of the message is this conditional entropy term. The maximum key size, as we saw, is given by this mutual information term. And so combining them, this is the general expression for the efficiency of this whole process, which is basically the amount of message bits per key size, per bit of key. So what I'm going to do now is actually get more analysis of this whole term to get some more insights about how it actually connects to the parameters of the system of physical parameters. Okay, so let me start with the following simple setup, where we have information, randomness sharing has happened. Alice and Bob have exchanged this unit symbol and got those Y and YB streams. And now for information reconciliation, what Alice does, it uses a simple two-level quantization scheme. So what she does is that there's a threshold tau such that if the current symbol is less than tau, then you actually quantize it as 0 or 1 otherwise. So what you actually get is just a stream of 0, 1 bits. For this particular scheme, what you can show is that you can actually compute analytically the entropy and this conditional entropy term. And so you can actually get what the efficiency is for a given tau. Now, let's see what happens if we keep changing what tau is. So this is a plot of that ratio R, which you could evaluate numerically from the previous slide. Basically, it's an analytical expression, and for a given tau, you can actually compute the exact number R. And then the x-axis is tau as I keep increasing tau. And also, as we saw, lower R is always better, because lower R means that you actually exchange less amounts of messages for every key bit that you get out of it. And there are three important observations that you make from this. First is that R actually decreases as tau increases. So on one hand, it's sort of intuitive, because if you're increasing tau, you're sort of making your quantization very coarse. So there are less errors between A and B. But what's happening is that you are also actually decreasing the amount of key that you can generate. But this sort of is happening in a favorable manner, so that if you look at amount of message that you need to exchange per bit of key, that's actually going down. The other thing that happens is that this R does not keep going down. It actually converges to a limit, and that this limiting value is non-zero. So what it says is that you can't arbitrarily keep reducing the amount of message bits that you need per bit of secret key size. There's a lower limit on that. And so this sort of, at least for this two-level quantization scheme, that point is sort of the best operating point. That's the point that you should sort of operate at, because it gives you the least amount of cost per bit of key that you use. What you can also do now is that using the expression that I had earlier, you could actually compute this limiting value, compute the limiting value in closed form. And this limiting value, you can see, it comes out as a function of the various parameters of the system, which are basically the variances of the fading coefficients, as well as the amount of interference power of the adversary. Also, one other thing that you can actually pull out of this thing is another interesting result, which is basically how does this limiting value, which is RL, compare with the correlation between the signals that A and B have received. So I'm going to define the correlation coefficient, which is standard correlation coefficient, which is between the received symbols between Alice and Bob, Y and YB. And you can show that this RL is nothing but takes this form. It's just inverse of rho square minus 1. So what this tells us is it's two very interesting results, which is basically that if rho tends to 1, which is that the two streams Y and YB are perfectly aligned, then RL is 0. Which just sort of makes sense, because if the two of them are perfectly aligned, then Alice and Bob to begin with have already perfectly aligned streams. They don't have to share anything or reconcile anything, they can just generate a stream. But as this rho tends to 0, your efficiency metric goes to infinity. You just have to keep doing more and more work for every bit of key that you extract. So this was all for the simple two-level quantization scheme. Let's now go to a more generalization, which is this general scalar quantization, where you choose some m levels and you choose some quantization levels q1 to qm minus 1. Again, for this, basically Alice quantizes in the following manner. If the symbol value lies between qi minus 1 and qi, you go to some quantization level I. Here again, for this scheme, you can compute what is the entropy term, conditional entropy term, and you can actually compute what the efficiency ratio would be given an n and given these quantization levels q1 to qm minus 1. Now, let's play the same trick again, which is what I'm going to do now is so in this plot, I randomly pick some m and randomly generate some quantization levels. And so each of these curves is a random m and random quantization level. And the y-axis is the ratio r, the efficiency number that you can compute. And the x-axis is some kind of scaling that I'm applying. The scaling is as follows. What I do is that all the positive quantization levels are just increased by some amount delta, and all the negative levels I decrease by same amount delta. So if I keep increasing delta, what I'm doing is that I'm just taking the center interval and just stretching it out. Essentially, I'm making the quantization more and more coarser because most of the mass will start to lie in the center interval. This is sort of similar thing that was happening with the two level, that you were just taking one level, one quantization level, and just stretching it out. Now, again, we see a similar trend, which is basically that as delta keeps increasing, these curves come down. So your efficiency improves as delta increases. So as you make the quantization more coarser, you are getting more and more efficient. Again, the value of r. The other surprising thing that happens is that the value of r actually converges, and all of the curves converge to the same point. In fact, you can also show that this is again more rigorously, that for any m-level scheme, start with any m-level scheme, if you take this delta go to infinity, then the limit that you get out of that is the same as the two-level quantization limit. So in some sense, it's saying, what this is saying is that at least within the space of the scalar quantization that we have looked at, you cannot do better than RL. RL is the best operating point for this setup. Actually, conversely, you can also show that RL is in fact the best lower bound that you can get. That given these discrete signal vectors ya and yb, no matter what transformation you make of ya, the number of information bits that you need per bit of secret key is at least r. So maybe I should just take a step back, and why am I trying to do all these things? Basically, what we are trying to do is to figure out that we want to understand how, what is the efficiency and function of the adversaries parameters, adversaries interference power. Now, if you choose any particular scheme, then the trade-off will be specific to that scheme. Now, when we go to this limit RL, what we are saying is that no matter what scheme you choose, you cannot do better than this. This is the best operating point. Now, let's look at the best operating point and understand what happens. So that's why I have this whole thing. I can pause for any questions. I hope this is too fast.
No, I can go back. A question on the previous slide. If you increase delta large enough, don't you recover the two case?
Yes. So that's sort of the question.
So you should expect to convert this. To going back to the previous case.
Yeah, that's sort of the intuition, but it's. I would say that's the intuition, but also have to rigorously argue that yes, that's the case. The point is that, okay, I'll tell you, what would happen is that these things could actually have started somewhere here, and they could have converged. So it's not clear, or you could have had this curve go down and then come back up, right? Those are all sorts of issues. So it's just scaling. The intuition is right. If you keep scaling, eventually you go to the two-level limit. But the idea is that the two-level limit is the best bound. You cannot do ups and downs in between and come to the same limit.
I guess that's the thing that I'm a little lost in. It looks like you're throwing away the constant. Why not just spread them out uniformly? so that as to preserve zero. I just don't understand how preserve the binning.
Okay. So you mean why is the uniform quantization?
Well, in this particular case, you're sort of making the center bin really big and throwing away all, and basically, essentially, effectively shrinking the others. Where instead of doing that, maybe perhaps spread them out evenly so that you still get the same sort of.
And have more and more bins.
Right. But how preserve the probability that you get a different quantization because you're essentially shrinking the probability that any of the other levels get touched.
Right. So, I mean, you would expect that. I mean, so what, yeah, so if you actually preserve the bins, then, or if you preserve the probabilities. So, one thing that's happening is that if I'm taking the central bin and expanding it out, I'm also decreasing the amount of key that I can generate, because what will happen is that others will just get a stream of zeros and occasionally will get a 1. So, the amount of key is going down. Of course, the amount of errors or the reconciliation is also going down. So, surprisingly, the idea is that actually doing that is better if you want to exchange the least amount of bit for every key size. So that's why this thing makes sense. I mean, you could argue that you could have a much more finer quantization and get a lot of more different symbols. What that will help you do is that it will help you generate the key that you want. Let's say you want a 256-bit key very fast, because every symbol that you get will have huge amount of entropy in it. But the thing is that there will be actually a lot of errors because there are so many bins, and B could actually fall into different bins than A, so you would also have to exchange more messages to get to that. The idea is that if you scale the center one, what you would have to do is that you would actually have to, you need a much longer sequence to compress it down to the size of the key that you get. So if you want, let's say, 128-bit key, you might need a much longer stream of Y's, received symbols, if you went through this quantization. But hope is that the amount of reconciliation also increases.
This is sort of the general case of the specific case of the general use for binary, because you get the maximum information per bit in a noisy environment with a two-level system. That's why you don't have three-state computers.
Right, but I'm actually just starting the binary, and I'm going to by scaling, I'm just actually going to a complete stream of zeros. So I'm going to a binary, 0 and 1, but then after going to a binary, I'm making more and more and more zeros, so changing the probabilities.
The original model involved these X signals being transmitted. So you're assuming in this that Alice is sending the same, sending the 1, and Bob is sending the 1 during that time period.
During the random.
And then Eve, you're also assuming is sending a 1.
It's sending an alpha.
It's sending an alpha.
Which is a
alpha time form.
Right, alpha times 1. And then we can, the idea is, let's see what happens when we change each in alpha.
Okay.
So ultimately we came to this limit, and the argument here was that this limit gives you the best trade-off between message sizing and message size that you need to exchange versus key size that you can generate out of it.
You're two levels. You have two quantization points, and then the threshold's halfway in the middle. You don't have a dead zone. You don't have a zone where we decide not to do anything. Because
in fact, there's only one threshold chart. Everything below or above.
Yeah. So 2 bins. So in a process like this where there's a zero mean process that both Alice and Bob are extracting, the problem is that much of the data is going to be centrally located. And if you're, say, your threshold 0, right, and the problem is that much of your data is going to be around that 0, and so it's quite likely, due to the fluctuations, that Alice is going to be on one side and Bob's on the other. So for that reason, a lot of us went to this sort of dead zone formulation. Have you considered that?
So this converse actually considers any kind of transformations. You could actually have a dead zone as well in between, so any transformation of y. The idea of considering the two level, the general level, was to show that this is actually achievable. Of course, it will get achieved in this. So when you have tau equals 0, you're right that you will fall on either side of the bin, and so you would have a lot of errors, and that's why you might have to do a lot of reconciliation for nothing because it's a zero bin process. So that's why if you keep making that threshold larger and larger, you might make one big very big, or one big very big, the other thing very small. But those schemes are sort of just to show achievability. Yes, you could come as much close as you want to this limit. Because you could have a lower bound which is just 0. I mean, anything also has. So this is sort of just going towards that. Okay, so this is sort of so basically whatever I've done in the previous slides is just to come to this limit RL. The two schemes, the two level and the general scalar quantization were just to show that achievability, that you could start with something and then come to this limit in some sense. But once you have this limit, what we're going to do is just try to understand how, if you keep changing these parameters in here, what happens to this number RL. So this is the plot of that. So I have actually, in these terms, I should have expanded this out. There's an alpha square term, which is the interference power of Eve. So each of these terms has some alpha square in there. And so this gamma is the variance between A and B. These are sort of slightly involved terms which have alpha square in them. And this is the plot where on the x-axis is alpha square, again in dB, and this is this value RL, which I'm just plotting. I've kept everything else constant. So for example, so this is sigma JB is different from sigma EA. This is the variance of the EA link, so variance of the EA link, variance of the EB link, and variance of the AV link, which is set to 1. N0 is just a noise term, some number 0.01. And there's an alpha square term which I'm just weighting on the x-axis, plotting this out. So let's see what sort of insights that we can get from that plot. The first and the obvious thing is that RL increases monotonically with Eve's power, which is sort of expected because as there's more and more interference power, you will have more and more disagreements between A and B. But you can also have some now quantitative numbers of what this would mean. For example, at 3 dB, RL is 24. So for every secret bit that you need to extract, you would have to exchange 24 bits between A and B. The other thing is that what happens, how does this curve actually increase? What's the rate of increase? That also you could sort of get out from that from the closed form formula of RL. And it turns out that the rate of increase is quadratic in Eve's signal power. So it's essentially RL grows as alpha to the 4, and alpha square is Eve's signal power. So it grows as E squared, Eve's interference power. So what's happening here is that if Eve increases its power by some amount, you're actually proportionally the RL increases in some quadratic fashion, right? So you're getting more and more worse off than Eve. And you can also compute order relationships about how this distance of Eve affect. So what we did here was that we fix a topology. Let's say A and B are on a line, and E lies in between. The distance between A and B is just unit distance, and so E lies anywhere on this line, and that's basically this distance D. So one distance, the distance of Eve, distance of Alice and Eve between Eve and Alice is D, and so the distance between Eve and Bob is 1 minus D. And you can get order relationship of this form, which is just showing that, of course, what's happening is that if you keep changing the distance D, in some sense the interference power is changing at Alice and Bob, but this is just showing as a parameter D what is this function, how does it grow? So basically 1 by D squared. And so the conclusion that you can get from this is basically that the performance of this whole key exchange process is contingent on what Eve's actions are. And in some sense, depending upon what Eve chooses as signal power, the performance of your scheme will get affected. And we just, we thought that this is sort of not a desirable property in some sense, because what will happen is that Eve might be able to control what is the efficiency of your scheme depending upon its actions. So some of the conclusion that we sort of gained from here was that the efficiency of scaling-based key exchange is highly sensitive to Eve's signal, external signal power, and it degrades rapidly, more specifically in a quadratic manner. And if you look at low noise environments, which is where things like below 0 dB, then yes, you could have a very reasonably efficient manner of generating the keys through wireless trading. But if you start to have higher and higher levels of Eve's interference, then you might run into issues of the efficiency.
So would Eve's best course of action be to directionally focus a lot of power or interference on one particular entity?
So those are sort of, that will actually make it much worse. Here at least so that will actually make Eve's efficiency of jamming much better.
Okay.
Ultimately what this is saying is that if you had the whole 3 steps, and if you had interference power, which is basically the power that each of these guys sees, which as pointed out was that you raise the noise floor, by focusing energy, you are raising the noise floor in a much better manner. So the next 3 slides are sort of, that was sort of an analysis of an adversary, which was just a very simple jammer. You could also think about an adversary which becomes a little bit more sophisticated. And one of the sophistications that we studied was this channel estimation. So basically what happens here is that, again, we have the same signal model, but now Eve can also know what the fading coefficients are on the links between A and E and B and E. And the way it can do that is that during the randomness sharing, when Alice and Bob are just sending energy into this environment, Eve can also receive that energy and can estimate, because Eve knows what the transmit signal of A and B are. So this is all public knowledge. This is happening as a public protocol without any pre-sharing of information, secret information. So Eve could actually estimate these fading coefficients. So let's just put the assumption that what if Eve also knows HE and HEA and HEB, so it sort of knows what sort of interference it's adding into the system. We can go through the same argument again and sort of argue that the message size, because Alice and Bob will go through the same set of processes, will be still the conditional entropy term. The amount of key now you can extract is different, because it's more specifically, it's sort of lower because Eve now knows something about the random sequences that Alice and Bob have. And so the new sort of metric, the expression for the performance metric, which is the message size divided by the key size, is this function. You can go through the same sort of arguments again. Let's start with the general quantization scheme. Let's look at these things. You can compute what these conditional entropy terms are, what the entropy terms are, and you can evaluate what this number R would look like. And then you can pick again let's say a specific 2-level scheme and take the limit again. Same whole process. Let's consider a tau and then take the limit as tau goes to infinity. Then you get a different expression for RL, which I've noted as RLC. So now you can see that these are the two different curves that are now going, which is one is basically just a simple jammer versus a curve for an adversary, which can also do channel estimation in addition to raising the noise floor. And we get sort of similar.
Adversary gets a channel. right now you're assuming sort of an omniscient adversary that happens to know the channel. But right now under your model, the channel coefficients, from what I see, are going to be independent with time, which meant that the only way it could have done a channel estimation was in the previous time interval.
So what I'm assuming is that is the following. When Alice and Bob are doing the randomness sharing, Alice will be emitting a unit symbol, and Bob will be just receiving the signal that comes to it. Eve will also get that signal, and Eve will be able to estimate because Eve knows what Alice is transmitting.
Yeah,
but Eve is also trying to insert interference. So this is sort of a duplex scenario for Eve.
right.
And the assumption is that possibly Eve could do that.
But if he's more than a few wavelengths away from the line of sight, he's not necessarily going to have the information to do that.
No, Eve's estimating Alice Eve channel, not Alice Bob channel.
Okay.
Oh, yeah.
Which brings up the other question. You're using random here. In a real environment, you have a lot of 2-meter structures, which are the size of people, and you have a uniform ground plane. There's a lot of regularity in the world. Doesn't that compromise the randomness? Is there an attack based on the fact that you've got vertical, orthogonal walls, orthogonal ceilings, flat floors, and there's a long-range coherence to the randomness in the channel?
So actually, you're right. You're perfectly right. So basically, you're arguing to the fact that look, besides these things that Eve could do, besides just having interference, there could also be other impairments, for generating the key through the fading process. And
It's sort of a Murphy's Law there, because out in the wild where there are no people, it's a fractal environment. But in places where there are lots of people, then you have people-sized structures, which are fairly coherent.
Yes.
Spatially.
yes,
The critique that we've been getting, particularly from the community, is that the present versus hard approach that you're presenting, really, somewhere in there's this assumption that the distributions are nice and symmetric about mean and so on.
Right.
Which is the Gaussian. Well, that is true if we all believe in Wusu's channels, but in reality, Wusu's is a nice general model, but no single environment is Wusu's. There's always
If I walk through this room, I get waka 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 waka.
Yeah.
I have in intervals.
But that's
That's a technical term.
well, I would just call it sort of
So, okay.
Let's hide that under the rug, right?
Okay.
So what we are saying is that suppose we don't have those other kind of issues, we have this type of environment, there could still be issues because of an activity.
Right.
I mean, of course. So that's pretty much what I had.
We just so did you get some sense of what the adversary should do? I mean, should the adversary try to focus more energy in the direction of Bob versus Alice because of something?
So I mean, if you, so you could argue that that there's adversary could actually maybe focus on one guy, the other might be better, but then could always switch roles, right? So what we are saying is that the adversary should just focus its energy during the randomness sharing process. If it can sort of raise the noise level, it will automatically create so much discrepancy that Alice and Bob will then have to again go through this whole, will have to exchange a lot of messages. And then when they're doing that, it can actually target communication of those messages. For example, let's say they have to use some kind of a MAC before sending out the packet, the adversary would just be very silent and just kill the MAC or those sort of things. So start by raising the noise floor. If adversary can figure out that they are starting this secret key exchange process, raise the noise floor, have them decorrelated to a large extent, and then.
I guess what I meant though actually is in terms of this part where you're discussing the adversaries estimating HAE and HEV. given a particular instantiation of HAB and HEB, it seems to be that probably there's some philosophy like the adversary should strategically choose to put proportionally more power into HEB if HEB is better, so that he gets more effectiveness at jamming Bob's side. And there's some nice water filling argument that can be done.
Yes. So yeah, we didn't sort of do that sort of analysis on that, but yeah, those things. I mean, we did observe that, it's actually a function of these numbers will be different, and so depending upon what so this plot assumes that the variances of both EA and EB links are the same, but what you're saying is that what if they are different? Then you could have another issue there. So we did not go into details of those analysis, but
So this is an ensemble result. I guess my question is about a single instantiation result.
And you have to move half a wavelength to get a different signal through by a lot.
So basically that's the summary that one thing that we actually, besides understanding the efficiency of this key exchange process using participating, what we also thought was that just looking at this notion of efficiency for wireless security protocols is also an important and interesting contribution, in the sense that mostly, what we observed is that, let's say, if you look at the security of the community, they sort of focus on getting stronger and stronger keys, better security. But then when you actually have this protocol run on the wireless system, you have all of these issues of communication cost, because you could have Adversary. And so this is sort of also, besides understanding key exchange, just this notion of understanding the efficiency of the protocol in terms of its communication cost versus, per bit of key that it gets generated, is also an interesting viewpoint that we thought came out of this work. And in fact, what we're trying to do currently with some of the research is to actually introduce, to apply this notion more generally to security protocols. So for example, you could think about a security protocol as sort of a flow chart. It goes through some steps, and then these steps actually get completed, and then you come to the conclusion where you have security established. And then through each of these steps, the node will may have to actually exchange some messages. And over a wireless channel, these message exchanges could either go through or they may fail. So there's a cost associated with that. And so you could now understand these security protocols with this cost in place. And some of the work that we're doing right now is to use some of the signal flow graphs where you again go back to the flow chart, you jump from one step to the next step, but these jumps are probabilistic. You may go to the step or you may not go to the step, and depending upon that, and also once you go to the step, there's a cost associated with it, depending upon how much power you put, and again, the cost here I'm talking about is the communication cost. So those sort of analysis that you can do, and also some of the things that we realize is that that these 5-layer techniques of utilizing trading and all that stuff is not just it can also be now incorporated into protocols which use computational cryptography to make those better, make more efficient. And so that's sort of some of the ongoing